Hi everyone, this is Group 35. This is a project included concept embeddings into vision language models. So current vision language models like CLEEP and BLEEP primarily operated at token level. While powerful, this token-based structure introduced two key limitations. The first one, it creates modality and language biases. Since models are tied to a specific linguistic structure, they often fail to be generalizable. Second, these models struggle to capture high-level abstract semantics, which are crucial for tasks involving reasoning and conceptual understanding. So motivated by this, our project aims to shift from token level to concept level representations by applying principles from LCMs to enhance abstraction reasoning and multimodal alignment in VLMs. Next. For text, to achieve this goal, our project includes three main components of methodology, data, and deliverables. On the methodology side, we take a hybrid approach for leverage Sona sentence embeddings as our context level textual representations and integrate that with large concept models. For data, we use COCO 27 datasets, include 180K images encoded with 5 captions each. And to summarize the deliverables, we got a mapping from vision encoder to Sonar embeddings and 4 pipelines for concept level image compactioning and VQA.
Okay, now let's go to the methodologies. So we train our model using a teacher-student framework. So we have this Sonar text encoder that produce 1024 dimension sentence embedding. And so our goal is to train an image encoder that uses a ResNet 50 backbone that also create a 1024 dimension embedding. We do so by trying to minimize the mean square error between the image encoder's embedding and the text encoder embedding. And so in general, our system looks like this. So for image caption test, we will input the image into the input encoder, which we do some transformation fusion, and then we use the decoder to create image caption. For VQAs, we have both the question input, which is text, into the text encoder of Sona, and then the image input into the image encoder we trained, and the output will be the answer to the question. For evaluation, we use cosine embedding loss, and we also investigated the mean square error loss. Here are some baselines. So for baseline, we try BLEEP on COCO. We get blue 4 of 39.2 and CIDR of 130.4. We tried two kinds of loss, the cosine embedding loss and the random caption mean square error loss. So the main takeaway is that the norm of the semantic embedding also matters, hence it's not ideal to use normalized contractive loss like cosine embedding loss or info NCE. Okay. So for conclusion and final direction, concept level or sentence level embeddings can capture higher order semantics. It does not necessarily follow a cosine similarity. And compared to contractive law, MSEs worked better. For future work, we plan to fine-tune a vision encoder with MSE instead and verify encoder with different metrics. We plan to apply the encoder for IM and VQA tasks to compare its efficiency to BIP, and we plan to integrate speech decoding also via Sona's multimodal decoder.